Well, first of all, it is a Big Bang model, and if otherwise, there is a Big Bang, but the Big Bang was not the beginning. The Big Bang theory suggests that the universe emerged out of nothing, signifying the beginning of the universe. Before this, there was nothing, no time, no space. However, what if I told you that time doesn't exist and that the Big Bang theory is incorrect? Recent discoveries made by the James Webb Space Telescope provide evidence that challenges the validities of the Big Bang theory. It turns out that the Big Bang wasn't the beginning of the universe, and in fact time itself may not exist. What's interesting is that this idea is supported by the renowned British physicist Roger Penrose. Now, you may wonder how the James Webb Space Telescope proves that time doesn't exist, and if the Big Bang theory is flawed. What alternative theories have been proposed to explain the origin and evolution of the universe? Let's delve in to find out. The idea that our universe has been expanding since its beginning over 13.8 billion years ago in a hot and dense state.
In 2018, Nobel Prize-winning physicist Roger Penrose claimed something very controversial. Roger Penrose had already baffled neuroscientists.
They have caused concern among cosmologists and astronomers. The surprise felt by experts stems from the fact that these images contradict the Big Bang theory. This theory has long been upheld as true by many scientists, so the new data has caused a significant upheaval in the scientific community. Astronomers like Alison Kirkpatrick from the University of Kansas are troubled by this development, questioning the validity of their previous work. The issue lies in the characteristics of the galaxies depicted in the JWST images. These galaxies appear unusually small, smooth, and surprisingly old. According to the Big Bang theory, as space expands, galaxies and other objects should appear larger as they move away from us due to the stretching of light. However, the JWST images show that the galaxies become smaller as the distance increases, which contradicts the theory. Even galaxies with greater mass and brightness than our own Milky Way appear 2 to 3 times smaller in the JWST images compared to previous observations by the Hubble Space Telescope. Additionally, the redshifts observed in these galaxies are also 2 to 3 times greater, further challenging the assumptions of an expanding universe in the Big Bang theory. These facts suggest that distant galaxies must be exceptionally tiny to account for this optical illusion, which is implausible. The presence of these small and smooth galaxies undermines the notion of expansion, thus casting doubt on the Big Bang theory. Supporters of the Big Bang theory were aware that their assumptions required the existence of these small and dense galaxies, often referred to as Mighty Mouse galaxies, based on previous observations from the Hubble Space Telescope. However, the JWST images have worsened the situation by refuting the idea that these tiny galaxies could grow into larger galaxies through collisions or expansion. The JWST images show well-formed spiral structures and smooth disks similar to the galaxies we observe today. This contradicts the expectation of mangled and distorted galaxies resulting from collisions. Without significant mergers, the tiny galaxies cannot become 100 times larger, indicating that they were not initially small. This finding challenges the optical illusion predicted by the expanding universe theory, suggesting that there is no expansion and consequently no Big Bang. The age and abundance of galaxies in the JWST images also pose problems for the Big Bang theory. By using infrared filters, the JWST can capture the colors of distant galaxies, allowing astronomers to estimate the age of the stars within them. According to the theory, these far-off galaxies should represent a time around 400 to 500 million years after the Big Bang. However, some of these galaxies show stellar populations that are over 1 billion years old, contradicting the assumption that nothing could have existed before the Big Bang. Certain ideas propose a cyclical nature.
There are actually two mysteries in quantum mechanics, and they get muddled. One of them is the whole subject is pretty crazy, yes. But it's coherent and it makes sense. And if
view for a block universe concept, where space and time are interconnected in what is known as space-time. According to a theory supported by Albert Einstein's theory of relativity, time and space are part of a four-dimensional structure, where each event has its position in space-time. This implies that everything, including the past and future, coexists in space-time, making them equally significant alongside the present. Physicist Max Tegmark from the Massachusetts Institute of Technology aims to address this concept. He suggests that reality can be depicted as either a three-dimensional space where events unfold over time, or a four-dimensional space where nothing changes. If the latter is true, then it implies that everything already exists at any given moment, encompassing the past, present, and future. However, we have an illusion that the past has occurred and the future is yet to come, leading us to perceive change. Julian Barber, a British physicist who has written extensively about time, offers his perspective on this matter. He describes our experiences as a series of nows and points out that we are only aware of our brain state. Our perception of the past arises from our brain storing memories. Barber refers to the space-time theory where each point in this conceptual country, which he calls Plutonia, represents a now. He suggests that what we believe is a past is merely an illusion created by our brains. This discussion brings us back to Albert Einstein's theory of space-time, which has caused some confusion in the field of physics. Scientists are now contemplating what would happen if Einstein's theory were proven incorrect. Would discarding the theory of space-time help us gain a better understanding of the universe? This would be a significant development. Throughout history, scientific revolutions have been crucial for progress. Dissatisfaction and doubts eventually lead to the emergence of new theories that replace the old ones. This pattern has occurred numerous times in the fields of astronomy and physics. Initially, humanity believed that Earth was at the center of the solar system, a belief that persisted for over a millennium. However, Nicholas Copernicus proposed a different theory, suggesting that it would be simpler to consider Earth as just another planet orbiting the Sun. Despite initial resistance, this heliocentric model gained support with the advent of telescopes. Isaac Newton also contributed to our understanding by explaining that the gravitational force of the Sun causes planets to orbit it. According to Newton, objects with mass exert gravity.
We don't fully understand how the universe began, which is often how people think about the Big Bang. That's a theory of how the universe began. It's not. It's a theory of how the universe evolved, assuming it already came into.
Introduced his general theory of relativity in 1915. This new theory successfully accounted for inconsistencies in the orbit of Mercury and was famously confirmed during a solar eclipse observation in 1919 off the coast of Africa. Contrary to Newton's idea of gravity as a pull, Einstein envisioned gravity as a consequence of the curvature of space. He proposed that all objects in the universe exist within a four-dimensional fabric known as space-time, and massive objects like the Sun curved this fabric, causing planets to follow the curvature in their orbits. To observers, this curvature manifests as a Newtonian gravitational pull. Einstein's theory of space-time has reigned supreme for over a century, overshadowing competing theories. The discovery of gravitational waves in 2015 further cemented its significance. However, like its predecessors, it may soon face challenges as it clashes with the other prominent theory in physics, quantum theory. The quantum world is known for its peculiarities, where particles can exist in multiple places simultaneously. In the 1930s, Erwin Schrödinger famously illustrated the strange nature of quantum superposition with his Schrödinger's cat thought experiment. It involved a sealed box containing a vial of poison connected to a hammer triggered by a quantum measurement. According to quantum physics, until the measurement is made, the particle exists in a superposition of both states, leading to the paradoxical scenario where the cat is simultaneously alive and dead. However, this picture of quantum superposition cannot be reconciled with a continuous and smooth fabric of space-time. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, acknowledges this conflict. According to Einstein's theory of spacetime, a gravitational field cannot be in two places simultaneously. It's influenced by matter and energy and is subject to curvature. However, quantum physics suggests that matter and energy can exist in multiple states simultaneously, defying traditional notions of locality. This raises the question, where does the gravitational field reside? Hossenfelder admits that there's no satisfactory answer to this question, highlighting the current challenge in reconciling general relativity with quantum theory. When attempts are made to merge these two theories, mathematical inconsistencies arise. Calculations sometimes yield probabilities greater than 1 or even infinity, which have no meaningful physical interpretations. Thus, the two theories are mathematically incompatible. LQG proposes a departure from one of the fundamental principles of general relativity, which asserts that spacetime is a continuous, smooth fabric. Instead, LQG suggests that spacetime is composed of interwoven loops, providing structure at the smallest scale. This concept can be likened to a length of cloth, initially appearing smooth but revealing a network of stitches upon closer inspection. Alternatively, it resembles a photograph on a computer screen made up of individual pixels when zoomed in. However, a challenge with LQG arises from the scale at which these defects in spacetime would be observable. Physicists define small as incredibly minuscule, with these defects only becoming apparent at the Planck scale, which is approximately a trillionth of a trillionth of a trillionth of a meter. The sheer number of loops within a cubic centimeter of space would surpass the quantity of cubic centimeters in the entire observable universe. Ultimately, the pursuit of a unified theory, combining general relativity and quantum mechanics, drives scientific inquiry forward. As researchers delve deeper into the mysteries of the universe, each contribution paves the way for future breakthroughs. What are your thoughts on these matters? Let us know in the comments section, and thank you for engaging in this discussion.